Hi everyone, my name is Tanaka. I am a mechanical engineering major, and today I'll be talking about the atomic force microscope enclosure. And my mentors this summer were Dr. Wocho Lee and Antoine Nguyen. So here's the agenda of what I plan to talk about today. And starting off with the background, at the Energy Transport and Conversion Lab, both Dr. Lee and Antoine do research to gain data from different nanomaterials. So different properties like mechanical, thermal, or electrical properties, and also some characteristics or traits, so they can determine if the surface of the material is smooth, jagged, or rough. And for this atomic force microscope to gain high-quality microscopic imaging, the microscope must be completely stationary when operational. So any small movements or vibrations that are absorbed by this microscope will actually cause some distorted imaging and invalid data. So figure 1.0 represents the high-quality imaging, and inside we have a red bordered box. And inside of that red bordered box we have some distorted imaging, and that's something we want to prevent. So here's the project goals. The main project goal for this summer was to design and manufacture an enclosure that was completely vibration-proof and soundproof for the atomic force microscope. So we then begin by choosing the parts for the enclosure, and then based off of those parts, we will then model them in SolidWorks to create a 3D model, and then move on to simulations on COMSOL. And then based off of the results from these simulations, we will then alter our total cost and also optimize our design. And then finally, the manufacturing process, so the assembly and fabrication of our enclosure. So here we have the overall specifications, the atomic force microscope and vibration table. The dimensions came out to be 500 by 400 by 550 millimeters. And then the weight of these two components came out to be 44.4 kilograms or 97.8 pounds. And since our enclosure is to be enclosing these two components, the dimensions of that came out to be 638 by 538 by 786 millimeters. And then the key factors for this enclosure is to be completely vibration-proof and soundproof. This is so that we can prevent any external acoustics or vibrations that are being absorbed by the microscope. And so here we have the methods of our design. So we started off with a general sketch that had the dimensions and a list of features that we wanted. And then we moved on to having 4 total designs for the enclosure. And so our first design, which is figure 1.3a, uses the highest quality materials and then the highest quality materials and the most features that we wanted, but this turned out to be the most expensive out of all 4. And then the second design, which is figure 1.3b, is similar to the first, except we removed some components to lower the cost. And then the third design, which is figure 1.3c, uses the similar methods as the first, except we lowered the quality of certain components to lower the cost even more. And then the figure 1.3d represents the fourth design, where we use the similar methods as the second to lower the cost even more. And then based off of these 4 designs, we can then gauge and determine which would be best in our situation based off of the cost and quality, while still maintaining the factors of being soundproof and vibration-proof. So here we have the methods of choosing certain parts and materials. So we have an example here of a decision-making matrices for a major component, which was the panels. So we had a list of options for the material to be the wood, the plastic, and then the metal. And then some mandatory requirements was these materials had to be easily manufacturable and then compatible with the T-slots. In some other categories, we also ranked these materials off of where the cost, sound absorption or reflection, the durability, if the thickness offered, and if the material was available locally or not. And then we then took these scores of these categories, summed them up, and then divided by 10 to receive our total score percentages. And then based off of the results, we can then say that wood would be best in our situation. And then this is just an example, so we did use the decision-making matrices for several other components as well. And so here we have the design, which is the third design. And for the framing, it is a T-slot framing that will be supporting our enclosure, and then surrounding that would be the plywood panels. The plywood panels will be fixed into place using nuts and bolts that will be mounted onto the framing. And then at the base, we have a mild steel plate, which will actually hold the atomic force microscope and vibration table. And then under this plate, we have a supporting beam to prevent any further deflection. And at the front of the design, we have a removable door. This is so that if researchers want to perform any experiments, they can easily remove or insert their material samples without any issues. And then at the base, we have some vibration dampening legs on all four corners. And to also get that soundproof factor as well, we implemented some acoustic foam. The acoustic foam will be on the insides, on the sides, and then on the top as well. But then on the base, we have it on the outside. And then the total cost for this enclosure came out to be $1,294. And so here we have more specifics of our design. At the base plate, we have some countersunk screw holes. And this is because if we were to use regular screws, the screw heads would actually extrude from the top. So when we place the atomic force microscope onto the plate, it would then be unbalanced. And that's something we wanted to prevent. And at the edges, we have some notches. This is so that the corners of the plate can actually hug the vertical T-slots to prevent any gaps from the bottom of the plate to the top. And then figure 1.6 represents the general dimensions of the enclosure. And then you can also see the components inside of the enclosure as well. So we have the soundproof material, the T-slot framing, the plate, and also a model of the atomic force microscope as well. So here we have a simulation, which is a static load simulation, and we used it to minimize the cost of the base section. So we started off with ranging our thicknesses for the plate from 10 gauge, which is about 2.5 millimeters, through 3/8 inch, which is about 9.5 millimeters. And then we also had 3 supporting beams, which we ranged from 1 to 3 as well. So for the objective of this simulation, we wanted to determine the vertical displacement caused by the atomic force microscope and vibration table when rested upon this plate. So we have the weight of these two components to be 44.4 kilograms, and then the base area to be 200 meters squared. And then we converted this information into a distributed load of 2.18 newtons per meter squared. And then the figures on the right, you can see we have a model with 1 supporting beam and then another with 3 supporting beams. Then the red arrows indicate the distributed load. The rectangle on the inside of the plate is the base area of the atomic force microscope and vibration table. And then you can also see we have some highlighted blue edges or faces. And this is actually where we fix the plate and the supporting beams so it wouldn't move in those areas. And so here we have the results for the simulation. The deflection displacement for the 3/8 inch plate, which is our thickest, came out to be 1.85 micrometers. And then the 10 gauge plate, which is our thinnest plate, came out to be 116 micrometers. And then the figure 1.9 represents the graph of the 10 gauge plate plotted with the total displacement versus the overall length of the plate. And this graph is plotted along that orange line on figure 2.0. And then based off of these two figures, you can actually see that the maximums occur right where there's no supporting beams. And this is to be expected. And then based off of the results, we can then say choosing a cheaper and thinner plate will be more ideal because the deflection displacement was quite neglectable. And so here we have the methods of choosing certain materials and parts for the base section. So we started off with 3 supporting beams. And then in our simulation, we then worked our way down until there was a significant difference in the deflection displacement. And that was when we noticed that 1 supporting beam would be good enough. And then so we had different material options for our plate as well, which was the A36 steel, which is our cheapest, the aluminum, which is our mid-range, and then the stainless steel, which was the most expensive. And then the main difference about all 3 of these materials is that the aluminum and stainless steel were quite lighter than the A36 steel. And since minimizing the weight wasn't our top priority, we then chose the A36 steel, also because of its price. And then based off of the information and then the simulation results, we then created the table on figure 2.1, which represents the deflection caused with 3 supporting beams, and then the deflection caused with 1 supporting beam. And then you can see we have the thicknesses ranging from 10 gauge through 3/8 inch, the price of each thickness, the deflection caused, and if this plate had any design conflicts or not. And this design conflict is represented by figure 2.2, where the base of the screw head actually extruded from the bottom of the plate and then touched the supporting beam. And that's something we didn't want. And then based off of that information, we then created another decision-making matrices for choosing the plate thicknesses. And then the range for the plate thicknesses ranged from 10 gauge through 3/8 inch. And then the categories, we ranked them off of were the cost, the deflection, and if this plate had any design conflicts or not. And then based off of the results, we then noticed that the 1/4 inch plate would be the best in our situation. And then here we have another simulation, which is a acoustic simulation, and we use it to determine the sound transmission loss onto the panel of the enclosure. So we had a range of frequencies, sound frequencies, from 10 hertz to 2000 hertz, and then we converted that information into acoustic pressure onto the panel. And then we also compared these materials of the panel from the plywood and then the acrylic plastic as well. And then figure 2.4 represents the model of the simulation. The red arrows indicate the acoustic pressure applied onto the panel, and then the blue area is the panel for the enclosure. And so here we have our results. For figure 2.5 represents the sound transmission loss using the acrylic panels, and you can see that the graph is quite slow compared to the figure 2.6, which is the sound transmission loss using the wood panels. The wood panels had a drastic loss compared to the acrylic plastic. And then based off of the results of these graphs, we can then say that choosing the wood would be best in our situation. And so we have the final design of our enclosure, which is the third design, and we choose this because of the simulation results, the decision-making matrices, the qualities, and then the cost of the enclosure as well. And so I'd like to close it off and give a special thanks to my mentors this summer, Dr. Wuchu Lee and Antoine Nguyen, and also the MANOA Design Clinic. Thank you. Please let me know if you have any questions.